चला गया। चलो
मुझे तो कोई दिखी
फ्रंट का कैमरा वो होगा ना कम पिक्सल
में और लोग हैं नहीं कैमरा पंकज पापा का नाम
बढ़िया
खाप जाली नहीं जाता इंजीनियरिंग कॉलेज का है अब आज मैं गए थे हाँ तो ब्रेक हुआ था
Ucua oleh mama ada buta
A very good afternoon and a warm welcome to all the honorable dignitaries, Dr. K.S. Pawar, Industrial Advisor, Honorable Chief Minister Uttarakhand, Professor R.C. Ramola from HNB Garhwal University, Professor Amrish Sharan Vidyarthi, Director, Nanni Pari Simant Engineering Institute, Pithoragarh, Convener, Dr. C.M.S. Negi, Co-Convener, Dr. K.C. Das, Organizing Committee, all the participants across India joining today's webinar on recent trends in physics, organized by NPSEI Pithoragarh. I, Mrs. Tarun Mahara, will be coordinating and moderating the session along with all organizing coordinators of the webinar. This webinar has been basically designed and developed to introduce you to some of the recent trends in physics, which we will be discussing during the course of today's session. As we have to basically go online and conduct all our teaching and learning online. So without taking much time, let's start the webinar, Essence of Ma Saraswati. Meanwhile, if you have any questions during the presentation, please type them into the question box in your Zoom control panel after the session. We will bring them up after the presentation and we will also have time for questions at the end. I would like to invite our esteemed guest, Professor R.C. Ramola, for a specialized lecture. Professor R.C. Ramola is Professor, Department of Physics, and former campus director of HNB Garhwal University, Tehri Garhwal. He has research experience of 35 years, teaching experience of 28 years, and administrative experience of 6 years as campus director. He has been honored with Bharat Gaurav Award in 2016 for his meritorious service, outstanding and remarkable role in science and higher education. He has also been honored with Dr. A.K. Ganguly National Award in 1995 for original and outstanding research work in the field of environmental radioactivity by Indian Association for Radiation Protection. Sir, we would like to welcome you to share your valuable knowledge with us. Sir, please.
Thank you very much. Am I audible to all? Hello.
Yes, sir, you are audible, sir.
Thank you very much for this nice word of the introduction. And I think before going ahead, I have to share the slide. So let me share the slide first and then we will talk. Hello.
Yes, sir.
Can you see the slide?
Yes, sir, yes, sir.
Yes, sir.
I've shared it. Okay, thank you very much and very good evening to all of you. And first of all, I would like to thank the organizers of this webinar and especially Dr. C.M.S. Negi for inviting me and giving me this opportunity to interact with different, I think, colleagues from different colleges and universities. So this is, the topic is basically the recent trends in physics. And today I'll talk something about the recent advances in the radiation research because I'm working on the radiation research for last, say, more than years, and I'll share some experience, especially on the ionization, and then of course the exposure, health effects, and some protective measures. And I think I have to check if it is working properly. I think there is some disturbance in between. The mic is opened or not unmuted, and I'm getting some voice in between. Hello. And now it seems fine. Anyway, I will start with this first slide, and you can see that there's some disturbance. I don't know why. Anyway, when we talk about the radiation, certainly we have a different kind of the radiation. And when you live on the Earth, you are surrounded by the radiation every time. So I'll keep my lecture more on the common side rather than the research side. And of course, we'll tell you something about our own work, but most of the time focus. Really sorry, I'm getting disturbed in between. There's some mic is opened and the sound, there are different kind of the sounds. Hello.
Sir, आपने सबको
Can you
unmute
please hear me?
Yes, sir. Okay, yes, sir, I'm doing. Okay, sir, I'm doing.
Yeah, continuously I'm getting disturbed and somebody is also playing with the screen. I don't know why. You can see somebody is playing with the screen and like this. Yeah, now I am unmuted. Okay. So we are surrounded by the radiation. And when we talk about the natural radiation sources, of course, we have the cosmic radiation. I will discuss one and each slowly and slowly. Then with the interaction of the cosmic radiation, we get the cosmogenic radionuclides, and then we have the solar radiation, you can see. And then, of course, we have the terrestrial radiation in the form of the various radionuclides, and then inhalation and ingestion. There are two different type of the process by which the radiation enters in our body. So this is a basic, the picture of the radiation, that how we are surrounded by the radiation. And this, I think, since this is a webinar on physics, I think most of you are already aware about it. That is the electromagnetic radiation. This is the spectrum, electromagnetic radiation. And you see that we have long range of the electromagnetic radiation, which is basically the difference is only wavelength or the frequency. So that extremely low frequency radiation is like, you can say, from that high, sorry, there is some disturbance again. It's disturbing me continuously.
We are muted all the participants.
Yeah, but I'm getting a sound continuously.
Sir. This,
Like this. Can you hear this sound?
yes, sir, I am also hearing this sound.
So this is disturbing. I don't know why.
So now, you are comfortable, sir? Now you are comfortable?
Now it's okay, but in between somebody is disturbing. I don't know why.
Okay, sir. Carry on, sir. If there is a problem, I will see.
Anyway, so I'm talking about the electromagnetic radiation. And you can say that when there is high tension, that electricity, they generally emit the extremely low frequency radiation. And these are some sources like very low frequency radiation from our computer, laptop, whatever is around you. Then, of course, the radio waves, which comes from the radio or the different antennas. Then nowadays, which is very popular, that is the microwave, which is the signal of our mobile, as well as some microwave which is used in the, and then infrared radiation is also there. Visible light, of course, we all know about it. That's the difference, is only that wavelength or frequency. And here there is a barrier in between. When we jump to the ultraviolet radiation, that is the ionizing radiation. And before that, this is the non-ionizing radiation. Now, the basic difference between the ionizing and non-ionizing radiation is that when this radiation, when it hits to any atom or any molecule, that molecule, that electron is emitted out and it gets ionized. So that is the main process which the ionization radiation plays, and that is more harmful, like ultraviolet radiation. X-ray, of course, which is used for the medical purpose, and gamma rays, you know, that is very harmful radiation. So this is a basic about the electromagnetic radiation. And if we go a little bit ahead about the size, then you can see that what is the size of this radiation. I mean, size means that what kind of the, what is the wavelength of that radiation, like the building and people, you can see that is the low frequency radiation. The wavelength is of the range of up to 10 to the power 3 meter. and so on. Like you can see, so I'm not going in detail about it. My aim was just to tell you that what is the difference between the ionizing and non-ionizing radiation. And these are some sources, and I think everybody knows about it, that these are the sources which are inside our house as well as the outside the houses. So these sources, they always emit the radiation. Now it depends on the frequency of the radiation, either it is ionizing or non-ionizing. But we are always surrounded by the radiation. That was my aim to tell you here, that we are always surrounded by the radiation, and that radiation is known as the natural radiation. This is the main thing. And then you can see, this is the average worldwide exposure to the natural radiation. And I'm really sorry if somebody is disturbing on that presentation.
Yes, I'm also hearing some problem, but I can't resolve this.
You can see that somebody is writing something on the screen also. Shall I share it again?
Yes, sir.
I don't know why, because that is disturbing in between. That is the main problem. Okay, let me continue. Okay, if there will be any problem again, I will share it again. Okay. So this is the, you can see the picture, that is worldwide exposure to natural radiation sources, and that is according to UNSCAR, United Nations Scientific Council for the Atomic Radiation. And this total exposure, which is equivalent to the 2.4 millisievert per year. And if you see out of this total exposure of 2.4 millisievert per year, the 55% of the radiation is just because of the radon or thorium. I will tell you what is the radon and thorium. And then the 6% radiation is of the terrestrial radionuclides, which you can say the uranium, thorium, potassium, and so many other radionuclides which are present on the Earth. And then internal radiation, which we generally consume in the form of the food stuff, it has the contribution about the 11%. The man-made radiation, I'll tell you what are the man-made radiation. And then cosmic radiation is about 8%. That cosmic radiation is quite important. So I'll tell you something in details about the cosmic radiation also. And medical X-ray, you see that man-made radiation is because of the medical X-ray. Then the consumer products, they contains the radiation, and then of course nuclear medicine, as well as some other sources you can see, which are very rarely used, but they also have some effect on this one. Now, if you see this medical scan, this is very common nowadays. Ultrasound is one, or MRI is one. It does not have any effect on the body because it contains zero radiation. And we compare it with the flying hours, like because when you fly on an airplane, then you are exposed to the cosmic radiation, and the radiation is very high. So that is equivalent to the 0 hours of flying. And when we talk about the low back X-ray, the X-ray is very harmful, if you say on that way. It is about 230 days of the natural radiation. 230 times you can say of the natural radiation, and which is equivalent to 182 hours of flying. So you can imagine that it is 182 times more than that ultrasound. And then CT scan is more harmful compared to that X-ray. It is equivalent to the 511 days of the natural radiation, or you can say the 462 hours of the flying. Now you can compare it, that the medical, it's not because nowadays we very frequently goes to the hospital and tell them that, okay, take my X-ray because I have this problem. Or even sometimes they frequently goes for the CT scan. Okay, I need the CT scan because I need to know more about it. But it should not be frequent until and unless some radiologist recommend it. You see that it is very high radiation, and sometimes it may cause some other effect on the body. So we must be very careful about it. So this is a normal one. And if you see this total radiation, as I told in the beginning, 2.4 millisievert per year. And as I told you that more than half is only radon, on 1.2 millisievert, and 0.29 millisievert per year is because of the ingestion which we consume. And then 0.39 millisievert per year is only the cosmic radiation, and 0.48 millisievert per year is external, or you can say the terrestrial radiation, which is present on our Earth. So now my screen, somebody has written so many things on it. I think you can also see it. Hello. Someone is really disturbing. He has written a lot of things on my screens. Hello. Anyway, if we talk about the early history of the natural radiation, I think you all know that the radioactivity was first discovered in 1896 by Henry Becquerel. And then after, between 1900 to 1902, the Oster and Gator measured the radioactivity in the atmosphere. And then between 1911-12, that the cosmic radiation was discovered. And that was a remarkable discovery again, because won the Nobel Prize for this discovery for the cosmic radiation. And the radioactivity is very closely associated with the age of the Earth. And here you can see that age of the Earth, there are different, the statement from the different people, like you know that William Shakespeare, and he has written that the poor world is almost 7,000 years old. And in all this time, there was no one, no any man died in his own, in the love cause. So this was his imagination, that the Earth is only about 7,000 old. But later on, the Charles Darwin theory, which predicted that it is about if not the hundreds, if not the thousands, but it is at least some hundreds million year old. That is, or more or less close to that geological discoveries or geological calculation nowadays. Now later on, the Calvin and William Thomas, they have also predicted, no, it is something about, they made 20 to 30 million year old. So that was another discovery. But the precise measurement was done when it was recorded by the radioactivity, that is by Rutherford. He dated the rocks. There is possibility to date the rock based on the radioactivity, because when you take a rock, it has some fission fragments, and then you put it to the neutron dosimeter, you can get some induced friction, and then you can find out what is the value of the age, what is the age of that rock, because the uranium isotope is very long-lived isotopes. It remains there for so many years, and it does not decay totally. You can decay it through the induced reactions, and then you can get the difference, and you'll find that what is the age of parts. So that way, when it was calculated with the radioactive dating, the date is about 4.55 billion year, and that is nowadays calculation based on the different geological or geochemical analysis, that Earth is about 4 to 5 billion year old. So this is also one remarkable work, that radioactivity can also predict the age of the Earth based on the dating of the rocks and some other materials on the Earth. Not only that, but sometimes we also do the dating of the meteoroids. If you get some meteoroids from the extraterrestrial environment, then we can also find out the date of that meteorites, and even sometimes the origin, if you know the geology and geochronology of that particular surface. Now, when we talk about the extraterrestrial radiation, so this is basically the cosmic. And this cosmic radiation, because atmospheric ionization is the important thing, which was investigated between 1900 to 1912. Because in 1886, radioactivity was discovered, and this was discovered later on. So in 1901, Wilson tentatively suggested the extraterrestrial radiation. Wilson suggested that there is possibility of some radiation which is coming from outer world. I mean, not from the Earth, but from outer world. And then in 1909, Wolf SJ, he measured ionization on Eiffel Tower in Paris. he measured that there is some radiation on the top of the Eiffel Tower. Now, where from that radiation is coming, that was also a question mark. Then in between 1909 to 1911, Albert Coquelle made a balloon flight and measured the radiation in the environment. And later on, that Domenico Ficini was an Italian scientist. He measured the ionization inside the water, and he found that there is also a possibility of radiation. There is also a contents of radiation inside the water. Everywhere radiation is coming out. And then in 1911, 1912, Victor has made a balloon flight and measured the cosmic radiation in the environment. So that is also another evidence that radiation is there. Now, this underwater ionization rate measurements were made by, as I told you, that Ficini in the June 1911, and he found that with the depth, he measured the radiation at the depth of 3 meters from the water surface, and he found that this value of the radiation, which was on the top of the surface, is less than 20% of that. And why it is less? Why it is decreasing? Because if we have only the terrestrial radiation, then the radiation should come from the ground. And if you take the ground below the water, if it is coming upward, it should decrease upward, not downward. That means if it is decreasing downward, that means something is coming from the top. And that top is nothing but that is the extraterrestrial radiation. So he made it clear that something is coming from the top of the earth. So this is one evidence. And another evidence, of course, as I told you, that cosmic radiation, which was measured by the Victor S. This is the equipment. He made a balloon flight and then found that this is coming out from the extraterrestrial environment. And this is one graph of the radiation. You see in the left-hand side, this is the graph that with increasing the height in kilometer from the surface of the earth, the radiation is increasing. And that is nothing but that is high energetic ions in the form of the cosmic rays, which are increasing. Or you can say that when you come close to the Earth's surface, this radiation is decreasing. Or on the other hand, you can say that when we talk about the high altitude, there is always radiation at the high altitude. So that is because we have the cosmic radiation at high altitude, and this increases with increasing the altitude from the Earth. In right-hand side also, we have someone is writing so many things on the screen, Hindi, Om, and so many things. Hello. Can I make a request to all of you, please do not disturb in between. Hello. I am sharing it again, please. So I was here. So that is the variation of atmospheric ionization with the depth of the atmosphere, or you can say with the height from the surface of the Earth. And I can tell you an example. This is how the cosmic radiation varies. This is cosmic radiation dose rate at different altitude. You see that at sea level, when we say that what is the value of cosmic radiation, it is about 0.03 microsievert per hour. When we come to an altitude about 2000 meter, like I have written here, Mussoorie, which is a nearby town here. So this radiation is about 0.909 microsievert per hour. And if you compare it with the global value, which is about 0.05 microsievert per hour, or on the other hand, because it is a different type of the unit, it is about 500 nanogray per hour. And then if you go upward, then 3900 meter, that is La Paz, which is a town of the Bolivia, the radiation is about 0.23 microsievert per hour. And if you travel through the international air travel, which is about 8,000 meters above the ground surface, it is about 3.7 microsievert per hour. And if you go a little bit higher, that is supersonic aircrafts, they fly at this altitude, and then it is about 13 microsievert per hour. So it is quite high at the, with increasing the altitude, it is increasing. And it can be seen from here that if it is an Earth, that is known as the Van Allen radiation belt. There is a radiation belt from 1,000 kilometers to up to 25,000 miles, or 1,000 miles to 25,000 miles. There is one belt which is known as the Van Allen radiation belt. And this belt consists of very high radiation in the sense that when any atom or any molecule which enters in this belt, all electrons are stripped out. And then they becomes the very highly high energetic positive ions, which are concentrated within that region. And this region is very important from many point of view, because all our satellites are in this region. Either it is geostationary satellite, or it is some geosynchronized orbit satellite, or some GPS station, all are surrounded here. And even if that space satellites in which our astronauts also goes, they are also exposed to this very high radiation. So this is very important, especially from that that space satellite point of view, because this radiation may cause harm to the instrument. This radiation may cause harm to the people in that satellite. And this radiation, it may disturb anything over there. So you have to be very careful that your instrument should be designed in such a way that it should not be disturbed with the cosmic radiation, because it is very high cosmic radiation. And this is a very wide belt. I told you that 1,000 mile to 25,000 mile. So this is the radiation, which is known as the cosmic radiation belt. And if you estimate the dose for the astronauts, the Apollo and Skylab mission, it is 1.2 to 1.4 millisievert per day. And then that International Space Station is about 150 millisievert per year. Just imagine 150 millisievert per year is quite high. And inside the spacecraft en route to Mars, because now we are planning to visit Mars, that is 1 millisievert per day. And on surface of Mars, it is estimated it is 0.64 millisievert per day. And if you make a visit to Mars, which generally take 180 days going and 180 days while coming back, and then if you want to stay 500 days on the Mars, who knows, in future we'll have this type of the opportunity. If the Mars mission is successful, then they will get exposed to 980 millisievert. So that is also quite high. So this that cosmic radiation is when we talk about this astronauts or air flight or whatever the space satellite, the cosmic radiation is very important, and we have to take all care to avoid this cosmic radiation. And if you say these are some levels which are compared with other values, this annual cosmic radiation on sea level, as I told you, it is not more than 0.2 millisievert. And the US average, all sources, is more than 3 millisievert per year. And that CT scan is more than that. It is more than the natural background radiation, which is about 8 millisievert. And then radiation worker. This is a very debatable topic nowadays, because for people we say that the safe level of radiation is only 2.4 plus 1 millisievert per year. That means it is 1 millisievert above the background. But for radiation worker, the limit is 20 millisievert per year. That means that is quite high. Then they calculate the hours, that how many times they have to get exposed with this, and like that. They fix the working hours so that they do not get exposed to high radiation. Then 6 months on that International Satellite Station, that average it is about 80 millisievert. This is quite high. And as I told you, 180-day transit on the Mars is about say 350 millisievert, and 500 days. This is more or less equal, either 100 days transit or 500 days on the Mars. So now let us come on the Earth, that is the terrestrial radiation. And you know that we have many area on the Earth having very high natural background radiation. As I told you in the beginning, that the exact value, the recommended value of the natural background radiation is 2.4 millisievert per year. But if you see here, these are some areas. Let me start from here. There is one area which is in Ramsar. This is Iran. You see that it is very high radiation background area. I'll show you some picture also. You'll find that how typical is it. That this is very high background radiation area, that you can say 10.2 millisievert it emits the radiation. Then Kerala area is also, this is in India. We have the Kerala monazite area in India. It has very high background radiation in that area because of the thorium in that area. Then we have in China also, that is very high background radiation area. Then we have one area in Brazil also. This is very high background radiation area. These areas are identified as the high background radiation areas. Of course, there is no clear standard definition for the high background radiation area, but the area having 20 millisievert per year or more radiation are generally categorized as the high background radiation area. So these are 4 areas. And then of course, there are many other areas having the high background radiation. Of course, not of that level, but high background radiation. So I will show you some slides here. This I got from one of my friends, Sorabi. He was the chairman of Atomic Energy Commission, Iran, and he lives in Ramsar. This is, you can see that a small spring, and it has very high radium contents. This spring has the very high radium content. This is the highest background radiation area in the world. And this, they measured it on the surface, that is the background radiation. And you see that dose rate at that place is 33.9 microsievert per hour. Can you imagine when you say that the background radiation all over the world is about 0.05 microsievert per hour, but this is 33.9. Or on the other hand, you can say the global mean is 42 nanosievert, and this is I will say that 3390 nanosievert per hour. So it's very high compared to that global average or global mean. So this is the house which is surrounded by the spring, and this is a teacher's house in Ramsar. And the important thing is he is always surrounded by very high radiation, but he is quite healthy and living over there very healthy. And this you see that the value inside the teacher's house is 108 microsievert per hour, which is again very high compared to that 0.05 microsievert per hour, or you can say the 56 nanosievert per hour. And it is if you compare that, 1080 nanosievert per hour. So this is again very high annual effective dose. And here high background radiation area is in Brazil, and the people used to go there to cure some disease, because the radiation it's a very, it's a very different thing when you talk about the radiation, because sometimes radiation is called as the harmful. On the other way, the people say no, it is very useful for the body, and you see that they are being treated with that Geiger counter with them, and they are using that sand, which is the monazite sand, to cure their disease or some other purpose. This is also high background area in Yongjiang in China, and they make the bricks in that area, and those bricks are of very high background radioactivity. And the important thing, or the worst thing, is that they use those bricks for the construction of the houses. So later on, it was found this area has the very high background radiation, and now they have discontinued this practice. but they were using the house sets with these bricks. And still there are many house sets which were constructed with the bricks of this hyperground radiation area. And then our Kerala area, you can see this is the beach area on the Kerala, and you can see it's a small picture, but you can see that a lot of people are there on the beach. And this beach has a very high background, like 70 milligray per year. It's very high background radiation, but people are living very happily there. They are also surviving there. Now, of course, now we have changed many things because initially we did not have any epidemiological study in that area, but now something has been changed. So this is one of the high background radiation area of the world. And in India, we have many high background radiation areas. And since people are already working on those areas, especially the Kerala coast, because this is the highest, this is having the highest background radiation. And now we have the cancer registry there, and so many other things are there so that you can have the epidemiological study as well as the dosimetric study. So there is one more area that is at the last, you can say, the Chhatarpur area in Odisha. And we have visited there a few years back, and we found that the background radiation is very high there. And then we thought to make some measurement there, and we have done an extensive study in that area. And I'll show you some results later on. But this is one area we have explored in 2009. And then we made some study in that area. This is the area, that is the Chhatarpur beach placer deposit area. Again, this is thoron rich area because it is monazite area. And these are the parameters, longitude, latitude, and then absolute gamma dose rate, whatever we observed there is 375 to 5,000 nanogray per hour. That is again quite high, about 100 times higher than the global average. So now let us talk about the basic of this radiation. You know that we have three important decay series. One is called as uranium-238 decay series. This is also the natural series also. That uranium-238 decay to different radioisotopes. And in between, you can say that you will see a blue arrow here, which is written radium-226. This is, of course, a highly radioactive element. And then it decays to radon. This radon is very important. It is important in the sense that this is the only gas member in the series. All other are solid. So this is only the gas member in the series. And once it decays out, it has a half-life of 3.8 days. That means within that 3.8 days, it may transport to any place. If it is within the water, it will be transported with the water. If it is in the soil, it will be transported to the surface through the evaporation, through the convection and different mechanism. That means it can travel a long distance within the earth and can enter in the environment. And once it enters in the environment, it has some harmful effect for the human being. So I will tell you what are those effects. And then another series is thorium-232 series, which we call 4N series. This is a decay series. That is the thorium-232. It decays to the radium, and that radium-224, when it decays, it forms the radon isotopes that is known as the thoron. The only difference between the radon and thoron is of its half-life. You see that its half-life is about 55 seconds. Precisely, you can say 55.4 seconds. And for radon, it is 3.8 to 5 days. So there's a big difference. So initially, it was assumed that thoron is not that much significant because it has very short half-life, and within 1 minute it decays out, so it does not enter the environment. But very recent studies, we have done some studies with the IAEA team and other team, we found that no, it is not like that. Sometimes thoron contribute the value more than the radon. So this is another isotope I will discuss. And this is third isotope, which is uranium-235 series, that is 4N plus 3 series. And here we have the radon isotope with 219. The atomic weight is 219. But the thing is, its half-life is only 4 seconds. And within that 4 seconds, it does not reach to the atmosphere and decay out on the surface of the earth or surface of the wall, wherever is it. So that does not travel to the atmosphere. That means it certainly does not have any contribution to the radiation dose in the environment. So we only have the two isotopes of the radon. One is called as the radon-222 and other one is called as radon 220. These two isotopes, I will tell you that how these isotopes are contributing the radiation in the earth. And as I told you in the beginning that more than 50% radiation is just because of the radon and thorium. So this one, I think this is a very basic slide, and especially for physicists, it's not that much important to discuss, because it shows you that why alpha is, how it was discovered that alpha is positive and beta is negative. That was the Rutherford experiment, that when it bends, and what is the range of the alpha particle, beta particle, and gamma particle. You know that alpha particle is, of course, an energetic particle, but it has a very short range. Beta particle is a little bit more because it is light particle, and gamma, of course, it is not a particle, but it is electromagnetic ray which can travel, which can penetrate even the body of the human being, and then it can cause damage inside the body also. And by that way, this is the simple alpha beta. This is the explanation that what is the alpha beta and how it has been measured, especially for the medical worker. That is a film, a badge is. They have, you can see here, the lady has a badge here, and this badge record all these radiations, and these radiations are in fact two types of the radiation measured in two different types. One is absorbed dose and other one is equivalent dose. Now here it is important when we say the absorbed dose. This is a physical unit. That means it gives you that the amount of energy absorbed by this mass, like 1 joule of the energy is absorbed by 1 kilogram of the mass. It is equivalent to 1 gray. 1 gray, initially it was RAD, radiation absorbed dose, but now the SI unit is gray. So but both are same. Either you say gray or red, these are the different one. So 1 gray, it gives you the absorbed dose. That what is the amount of radon absorbed by a particular substance. Now equivalent dose is biological unit. This is the difference, main difference. This is the biological unit. That means what is the effect on the tissues of the body due to that radiation. That is measured in terms of the sievert. And this was initially, it was RAM, Roentgen equivalent man. That means 1 Roentgen equivalent man means 1 Roentgen of the X-ray. That is, if the damage is equivalent to the 1 Roentgen of the X-ray, that is known as the 1 Roentgen equivalent, 1 RAM. And now it is sievert, is now SI unit is sievert, so it is written in sievert. So these are two doses, so one should not get confused that what is the absorbed dose and what is the equivalent dose. One is physical unit and other one is biological unit, which tells you about the damage caused due to the impact of the radiation on the body or on the tissue or on the cell. So this is how we calculate. This effect is not always same. It doesn't mean that suppose there is 1 gray of radiation and when it enters in the body, it will create this particular amount of damage. It's not same, because every organ of the body has a different weightage factor. For example, if I say the liver will have the different effect, maybe 1 radiation, 1 gray of radiation will have more effect on the liver compared to the heart, or more effect on the heart compared to the liver. So then there is one weightage factor also, because that is known as the equivalent dose. And equivalent dose, for example, I have written here 1, WT1, WT2, WT3. That gives you WT1 is the impact on that particular organ. WT2 is the impact on that second particular organ. And WT3 is impact on that third particular organ, which is known as the effective dose on that particular organ. And when we talk about the equivalent dose on a body, that gives you WT1, WT2, WT3, and it depends how many weightage factors are there, how many organs are being disturbed with this. And then you can say that this is the equivalent dose in terms of the sievert on the body. So it is entirely different. Absorbed dose, I told you that that is the amount of energy absorbed by that particular object, particular body. And equivalent dose is the radiation that is damage caused on the body. because generally people get confused about it, that what is gray and what is severed. So one is physical unit and other one is biological unit. And if you see the ionizing radiation, where it affects, there are many areas, and which are the isotopes which affects the body, like the iodine-131. And you might have heard about the nuclear accident, and very recent one was in Fukushima. And then there was a report that they used to measure the iodine, because the iodine is released in the accident, especially the iodine. Of course, it has half-life of 8 days only. Iodine and cesium are two isotopes which are released in very large amount during the nuclear accident. So iodine, it affects the thyroid, and especially for the children, it is very dangerous. So if there is some iodine in the atmosphere, especially when after that nuclear accident, then the thyroid is also the target. That is important. For skin, of course, sulfur is there. For lungs, radon is there. I'll tell you that how radon is important, because radon is basically an alpha emitter, and it creates the damage inside the lungs when it enters inside the lungs. And then liver, the cobalt is one isotope which is generally used in the laboratory also, you know about it. That caused the damage to the liver, and this is the beta emitter. Then the spleen also, polonium-210. All these isotopes, you can say that ruthenium, that is gamma radiation, that is very harmful for the kidney. And for ovaries, of course, all these isotopes, iodine, cobalt, krypton, potassium, cesium. Cesium is, because cesium is considered to be more dangerous after that nuclear accident, because cesium has a half-life of about 30 years. And once it enters in the environment, it remains there for 30 years. And if it is in very, it has a very high concentration in that area, so it will continue expose that particular human being or the particular part of the body. So that cesium is quite harmful. And then for bone also, radium is also harmful, because when it enters in the bone, that also creates some problem. And for muscles also, potassium and cesium, again, this is harmful for these areas. And if you talk in terms of the effect, what kind of the effects and what is the symptoms of the radiation, like for brain, a headache, nausea, fatigueness, and fainting, weakness. And of course, hair loss is also there. That is the symptoms of the exposure of radiation. Mouth area, there are symptoms like inflammation on the mouth, throat ulcer, and then enlarged thyroid glands, that is for the thyroids. For heart also, these are different symptoms. For lungs also, there is possibility of the lung cancer also. Stomach also, what kind of the symptoms are there. And skin, inflammatory skin, bone marrow. So every part of the body is affected by that radiation, and there are different type of the symptoms for the radiation. And if you talk about the level of the radiation, this radiation effect, so tolerable level is up to 20 millisievert per year. That is the yearly limit. And as I told you in the beginning, that 20 millisievert is permissible for the radiation workers, because the radiation workers, they work up to the 20 millisievert per year level. And so that is a tolerable level, and it does not have, major impact on the body. Of course, it has the impact, but it depends on the length of the exposure also. Suppose one person is being, hello? Hello? Can you hear me? Hello? Hello? I don't know if I'm connected. Hello?
Hello?
Can you hear me?
Yes, sir.
So I'm connected. I thought I'm disconnected. So I'm talking about the
Hello?
tolerable level of the radiation. And this tolerable level of,
बोलो
hello?
अभी बंद
The tolerable level is up to 20 millisievert per year. And then risk.
Hello.
Hello?
Good afternoon, sir.
Yeah, please.
Yeah, I can hear all the things.
Yeah, okay. I was just checking if you are hearing me, because in between I thought
Okay,
that,
okay. Thank you.
okay, it's okay.
Okay, sir. Okay, sir. You continue.
Okay. So then we have the moderate risk. And moderate risk is from 100 millisievert to say 1000 millisievert. And this is, of course, there are no immediate symptoms, but it increases with the risk increases, and later on in the life that serious illness may be created, because once they get exposed to this very high radiation, there is possibility that some symptoms will be developed maybe after 15 or 20 years, and then there will be some problem. And then acute, or you can say the high risk, is above 200 millisievert radiation. And this is assumed that if that is the fatal radiation, if somebody exposed to this radiation, especially in case of the nuclear accident, so this is the fatal radiation, or nuclear bomb also, these are the fatal radiations. And then the death is sure in that case, if somebody get exposed to this radiation. So this is the basic idea about the radiation, that what is the level of radiation which is tolerable, or which is the moderate, or which is the fatal. And these are different, of course, again, the same thing, you will see that how this radiation affects the bodies or different parts of the bodies. So I'm not going to repeat it. Now I'll come to the radon, thoron, and their health consequences, which I discussed in the beginning, that there are two isotopes of radon, radon 222 and radon 220. So now what are those isotopes? You can see radon 222, of course, the atomic number is 86, and this is about the phase of radon is gas, as I told you. The same thing with the thoron also. So these are two isotopes which are result of two different decay. And this radon 222, now I would like to say here that radon itself is not harmful. This radon 222 decay in polonium-218. As I told you, that radon is a gas having the half-life of 3.82 days. Now, when it decay out from the radium, it enters in the environment, and it get attached with the aerosol also. And then with that, it comes to the environment, and it enters inside our lungs with the inhalation process. So of course, there is always a possibility that when it goes inside, it will also exhale out. It may also come out, because the half-life is quite high. But if that radon atom, if it decay inside the lungs, then immediately it forms the polonium-218. And polonium-218 is again the alpha emitter, and it is a solid progeny. Then it does not come out. It get attached to somewhere, and this polonium-218 has the alpha emitter having the energy of 6 MeV, and 6 MeV energy is quite high. So whatever the part of the cell or the tissue comes in contact with that alpha particle, it get irradiated with that particle. And then within next few minutes, it again decay to the polonium-214, which again decay to the alpha particle. Decay the alpha particle, and then 7.69 is the energy of that alpha particle. So you can say that within few minutes, that tissue or that cell, it gets 2 alpha particles of the very high energy, like 6.0 and 7.69, 2 alpha particles of very high energy. And then, of course, it decays to the lead-210, which has the half-life of 22.3 years. That remains there for a long time. And as I told you in the beginning, that there is also possibility that after 20 years, the radiation will be increased at that particular part if it remains there. And then it may goes to the polonium-210, and then again the alpha particle. And you know that body has the tendency to recover. If there is a damage, after some time it will be recovered. But if the damage is more than the recovery, then it will continue to increase the damage. And with the time, it will become a cancer. So that's why radon 222 is known as a cause for the lung cancer. So that's why it is quite important to study. And if you see the thoron, as I told you that in beginning without thoron is not harmful. But you see, when thoron decay out within say 55 seconds, the polonium-216, that atom is formed, which immediately decay to lead-212. This is the alpha emitter. But this lead-212 has the half-life of 10.6 hours. Now, what happens actually, that this lead-212, it has the half-life of more than 10 hours. It may get attached with the aerosol. And this aerosol, which is circulating inside the room, this lead-210, it again decay to polonium-212. Lead-210, it decay to bismuth, and then bismuth decay to polonium-212. And when polonium-212 decay, it is an alpha emitter. It has the energy of 8.78 MeV. It is the highest ever energy of any alpha particle within that series. So if any tissue comes in contact with this alpha particle, that will be the high impact compared to the radon alpha particle. So that means the equal amount of radon and thoron will give a different value of the dose. And it will have very high value. I'll show you what is that factor. It will be very high compared to the radon. So if we have the thoron concentration, especially as I told you that we have thorium deposit in India, of course, in the southern peninsula, we have many areas with the thoron deposits. And when the person come with the thoron in that area, there is possibility that the thoron, they are exposed with the thoron, and there is possibility that these lung tissues and any other tissues are being hit by this high energetic alpha particle, and that may cause the damage. So now this, I intentionally put it in many times because it is very encouraging slide, especially for the young researchers. This is a statement made by Patrick Blackett, who was working on that cosmic radiation and discovered the cloud chamber. He got the Nobel Prize for that because it was related to the discovery of thoron. In fact, when radioactivity was discovered, the Rutherford was making an experiment in the laboratories for some transition of the element. And then in the evening, when you go out and comes back next morning, he found that there is something very unusual. Unusual in the sense that, because it was discovered accidentally. Unusual in the sense that in nighttime, he was getting very high values. And then once he opens the door, this goes down. So initially, he could not understand what is this. They thought our instrument is not working. And their students also, they thought, no, it's not working. Let us try to repair the experiment, try to repair the instruments. But with the time, they observed, no, it's not like that. It is something which is affecting the instrument in the night, and especially when you close the door. And if you close the door, that means something is being accumulated inside. And then later on that they found that it is not the fault of the instrument, but it is a gas which is disturbing the counts of the instruments. And that gas is a radioactive gas which was discovered as the thoron. And in fact, thoron was discovered before the radon. That is very important. And then they discovered, no, this is a gas which is radioactive. And first time it was discovered that there is possibility of an element which is in the gas form and is radioactive. And later on it was found, no, it is a member of the series. And then they discovered the radon as well as other isotopes of the radon also. So this is very encouraging statement by Patrick Blackett that one should not give up. Suppose you are not getting any result properly as per your expectation, that result is also a result. One cannot say that this is a wrong result. Wrong result is also a result. So you should not discourage with the wrong result. For example, if you say, no, it should be, if it is not as per your expectation, that means that is also a result. You should try to find out why it happened. So there should be always encouraging pattern that result is always result. of course, this simply the Rutherford. I just want to show you some photographs. This is a very, important photograph. You can see in center with the cap in hand is J.J. Thomson, you know, the famous person for the discovery of the electron. This is Rutherford, and just behind these two, Madame Curie. These three eminent personalities are all together, and there are many others also. But these are three Nobel laureates together because there was a conference in McGill University in Canada. So this is one of the rare photographs. I have put it here. Now the thing is, when you see the radon, now the thing is, where do you find the radon? I'll say that it is everywhere. Even the place I'm sitting here, even the place you are sitting in your home, everywhere radon is present. Because the uranium is omnipresent, it is everywhere distributed on the earth. So if uranium is there, definitely there will be radium, and if radium is there, radon will be there. It depends on the locations, either it is high or low. Otherwise, radon is everywhere. Wherever you go, you'll find radon, either in the form of radon or thorium. So this is one a sketch I got from the web, that is Science Talk about the radon. It was very simple. That okay, we'll discuss about the radon today. That it is found in rock, soil, and water. It's everywhere. Either you talk the rock, you talk the soil, or you talk about the water. And of course, it is a product of the decay series of uranium-92. This is general 238, 235, whatever is, but it is a decay product of. Then it is harmful for the lungs. You can see here the lung cancer. It may cause the lung cancer. Then it is tasteless, odorless, and colorless. You cannot taste it, you cannot see it, it's tasteless, odorless, and you cannot smell it. And then it is generally inside the house, it is accumulated, or not only inside the house, I would say the closed spaces. If you go in the field, caves or many things, it is generally accumulated in the closed space. And these are different risks and benefits of radon. I will not go in detail. It is used for the uranium exploration. It is used for the geological application, geohydrological application. We have also used for the earthquake forecasting. And then there are different methods in environment, contemporary method, retrospective methods. So I'll not go in detail. I'm just telling you the basic about it, that what are these. And then when we talk about the reference annual intake in food, water, and air, you see that this is the consumption for the infant, children, and adult. And you said the maximum amount which we take is the air. That is as a result of the breathing. And if we talk in terms of the value of the breathing rate, meter cube per annum, an infant consume 1,900 meter cube per annum. The children, they inhale 5,600 meter cube per annum. And an adult, they inhale 7,300 meter cube per annum. That means the maximum amount which we consume or which we intake to the body is the air, and the radon is present in the air only, and that's why it goes in the lungs. So this is the reason that radon affects the lungs only. And if you see in terms of its effect, everybody knows that smoking is the highest, or you can say the major cause of the lung cancer. Smoking is there, and radon is the second major cause after the smoking. And if radon and smoking is combined, see in the right hand side, I put one one analysis, that is the lung cancer risk. A smoker plus high radiation, then 1 out of 3 will get cancer definitely, if one is a smoker and also getting the high value of the radon concentration. And if he is being exposed, he or she is being exposed to the radon only, and he is non-smoker, then 1 out of 20 will get the exposure, and 1 out of 20 will get the lung cancer. So that is the frequency of the lung cancer, you can say, with the smoker and without a smoke. And there are some other reasons also. I'm not going in detail that what are those, but my concentration or my focus is basically on the lung cancer due to radon, which is second after the smoking. And as I told you that we are breathing the radon maximum, so it enters inside the lungs, and this is the process how it enters, because radon atom, it decays to radon decays and it get attached with the aerosol, and that aerosol is always distributed in the environment, and when we inhale it goes inside the lungs, and then ultimately you get the value of radon concentration. And as I told you that it is generally accumulated at the places when we have very the closed environments like this, and these are some areas like how this enter inside the room. Basically, the radon comes from the ground. Of course, that building material is also a cause. It depends if you have building material from some areas where we have the very high concentration of the radon. But generally, it comes from the cracks, joints, walls, or gaps in between when it is exposed to the ground. That radon it enter inside the house, and then it is accumulated there, because if you see that in industrial countries and even in the cold climate in India, because the high value of radon is generally in cold climate, because we keep our doors or windows closed most of the time just to conserve the energy. And this radon, once it enters inside the house, it does not go out easily. Only when we open the room, there is a ventilation. So ventilation is main thing. So now let me talk about some international scenario of radon issue. This is again a rare photograph I can show you. This is Madame Curie in between, you can see, and this is the iron, that Jatismal iron, which is in Czech Republic, and she worked there. And I think you know that she got Nobel Prize twice, one in physics and one in chemistry. And the very important thing, I don't know if you have an idea that there is Curie family got 5 Nobel Prizes. That is the rare honor or rare thing in the history of the science, that Curie family got 5 Nobel Prize, 2 Nobel Prize by Madame Curie, one by that Marie Curie, husband of the Madame Curie, which was shared by the Madame Curie and Marie Curie. And the third one is, the fourth one is by the daughter of Madame Curie, and fifth one is by son-in-law of Madame Curie. So it was a very different story that 5 Curie family members got Nobel Prize. So this is just to show you that this is one rare photograph. And the uranium mine, in the right-hand side, you can see the uranium mine. So she worked inside that mine throughout the life. And you know that at the end, she also died because of the cancer, because of that radium. And this is the history of radon, because initially, I'm not going in detail. Initially, it was thought that there was a very high mortality rate of the lung disease in the uranium mines. They did not find what is this. It was observed that no, whosoever work in the mine get the lung cancer. But later on, after the discovery of radioactivity, it was found that that lung cancer is because of the radon, and that radon is later on identified by UNSCEAR and ICRP, and then certain recommendation has been imposed that one should not get exposed and one should not work more than this time inside the mine, or one should have all protective measure to enter inside the mines. So that was one issue. And later on, very recently, I will say, in 2004, World Health Organization has also entered in the business, because initially it was that United Nations work and International Council for Radiological Protection. But when they found that it caused serious health consequences, then World Health Organization has given some recommendation. They framed a task group to give the recommendation. And there was different recommendations from the different group, and World Health Organization has given a final recommendation. They published a book, that is a WHO Radon Handbook. And this was focused on the radon prevention in new building, because there are two types of the buildings. One is new building, when you construct a new building, and other one is mitigation in the existing building. Because in new building, of course, you have to construct in such a way that you should not have the areas or have the construction in such a way that the radon accumulate inside the house. And mitigation means, suppose you have observed very high radon concentration in one house, then you have to find the way to mitigate or way to minimize the concentration of radon, because ICRP has first given one recommendation that in new building we should not have value more than 200 becquerel per cubic meter, and in existing building you should not have the value more than that is 600 becquerel per cubic meter. So WHO has given a limit that in any case for new building the value should not exceed 100 becquerel per cubic meter, and old buildings should not have the value of the value more than 300 becquerel per cubic meter. That means if an old building have more than 300 becquerel per cubic meter of the radon, then they have to go for the mitigation. They have to go for the remedial measures. So this is the WHO recommendation, and now it is existing nowadays. Now everybody has to follow it everywhere in the world. And we are lucky enough because our in India, if you see, our radon concentration average value is 25 becquerel per cubic meter. So we don't have that problem of radon problem in India. But once you enter in the hill area, because I am working here in Garhwal and Kumaon, Himalaya, we made some measurement here, and we have many areas having the value up to 200 or 400 becquerel per cubic meter. Of course, we have reported it, and we have also, we try to find out what is the reason for that. But we have many areas over here. And if you go in the south, again, you will find a very high concentration of thoron concentration, which has a direct impact on the people. So these two values or these two areas have to be identified, and more studies required in these areas. But in general, if you talk about in general about India, we don't have the problem of the radon because it is a tropical country, and we generally have very well ventilated houses, and that's why it is not accumulated inside the house. And if you go in the Europe and America or Canada, you will find that all are the air conditioned house. They are always closed because more than 8 or 9 months they have the cold climate. So that's why they have the very high values, and they have to reduce it up to the 100 becquerel. Then ICRP, these are some recommendations. I just put these files here. International Council for Radiation Protection. They work on these conditions. And then, of course, there are different type of the situations. One is planned exposure situation, emergency exposure situation, existing exposure situation, and norm is one. That is the naturally occurring radiation material. Radon is one of them. And then you get that reference level is planned on based on this, that what is the value of this, what is the contribution of these, all these parameters. And then reference limit or reference level, or you can say the dose limit, can be calculated for the different area. And we generally have two different approaches. One is unscared approach and other is ICRP approach. That ICRP approach, this is that epidemiological approach. And this epidemiological approach is that the past history of radiation, like atom bomb survival in Hiroshima and Nagasaki. The atom bomb survival, they studied the effect of the radiation on the atom bomb survival, and then measured it that what is the effect on the people nowadays. And this dosimetric approach is different. That is basically based on the animal experiments. They get the animal exposed and then find the effect. But when you come on to this final conclusion, you will see that unscared value generally gives higher values, the dosimetric. And now there is a debate that we should have come to one conclusion that it should be same value, either epidemiological or that dosimetric model. So now I will not discuss it. This already has been discussed, that the WHO handbook has given us the limit is 100 to 300. Initially it was 200 to 600. So it was reduced just half. And then based on the ICRP and NCRP, then they prepare a basic safety standard, IAEA, you might have heard it, that the International Atomic Energy Agency. They prepared the safety standard and then publish the recommendations. And if you see, as I told you in the beginning, that thoron is very dangerous compared to radon. because the estimated if one is getting exposed to 1 becquerel hour per meter cube, then he will receive the dose of the 9 nanosievert. But if one person is getting with the 1 becquerel hour per meter cube of the thoron, as I told you that it has high impact. The impact is more than 4 times. It is 9 nanosievert and it is 4 nanosievert. That means the exposure of thoron is more harmful compared to radon. Initially, we ignored it. Say about up to 2005 or 6, we ignored it. No, it has very short half-life. But after 2005, we have started some work on it. Of course, I am also a part of that to this encourage the thoron study, because we initiated it in 2005 with a workshop in Serbia in the very high background radiation area. And then we found that no, thoron is also contributing. It is not only radon, but thoron is contributing more than radon, sometimes more than radon. And if you talk about the USA, radon in USA, you know that they have 1 month, January they call radon action month. You have to record or you have to measure the radon concentration inside your house and then report to government. And based on that air quality control, that department will come. If your house is within the safe limit, that's not a problem. Otherwise, you have to get it ready for the remedial action and you have to renovate it so that the radon concentration will come within the safe limit. So that is a part of daily life, you can say, of the radon concentration in USA. And the important thing is that you have to give a certificate before constructing the house, and then again record the concentration of radon inside the house after the construction. And only then you will get the possession of that house. You can enter in the house when you declare, or when the certifying agency declare that this house is radon free, or this house doesn't have radon concentration above the recommended level. So this, as I told you, that we are measuring the radon concentration and thoron concentration in Niška Banja, that is the Serbia. And I was working with the IAEA team, and we found a hotel there. And this is very surprising. I put this photo because the hotel's name is Radon Hotel. So we have inquired why it is the Radon Hotel. Then we found that they have a spring having the very high radon concentration, or you can say the very high radium concentration, and they treat the people there. That is, there is an spa, then water the radium concentration is very high, and they treat the people there for different disease. And this is the hotel, they get the treatment there. There are many areas, of course, I'm not talking in detail, because there are many areas in Europe that they use radon as a treatment for different disease. So this is one hotel which is used for the treatment of the disease based on the radon concentration, and you see it has very high radon concentration. Radium concentration is 1810 becquerel per cubic meter, and gamma radiation dose is 316 nanogray. So that is quite high, but that is one. And of course, we made the measurement there, and this is the result of that measurement that we have published here. And then later on, when we were working on the radon and thoron, so we realized that when you see that ICRP and unscare value, which is mainly for the radiation dose, I think I can take next 10 to 15 minutes. So when we talk about the radiation dose, so most of the recommendations are based on the work done in Europe or in USA. But at the same time, if you see, we have very high background radiation areas in Asia, like Iran is also in Asia, India is in Asia, China is in Asia. And when the radiation dose were calculated, there is no reference of the Indian data. That was the main problem. Then in 2009, we thought, because from China, Japan, and from Korea and Thailand, and from India, of course, we thought that let us make a joint research program for the natural radiation exposure, and we'll submit the data to UNSCARE and ICRP, so that we should have the contribution of the Indian data also. Then in October 2009, we had a meeting in Japan, about this recommendations or this project. And we had a project for 3 years, and 5 countries were collaborating in that project: Japan, China, Korea, Thailand. And from India, I was coordinating. And all possible measurements are tried in all countries at different places, like manometry technique. I will not discuss detail about this, but I will just show you the photographs. These are some AlphaGuard. This is very sensitive technique for this indoor measurement. Red 7 for the Thoron. Then some indigenous techniques also. Bhabha Atomic Research Center had developed them. And then these are some for the large scale survey. And this is for radon, thoron, progeny concentration, attached, unattached fraction. All possible methodology has been used. This is for the thoron measurement, thorium that to trap that polonium 212 atom. This is for the instantaneous measurement. And of course, we need that pocket survey meter for the gamma ray spectrometry. And then this GPS for location identification. So all these, we in India, one part I also, of course, this is the Odisha area, the eastern Odisha, as I told you in the beginning, that these are some houses. You can see we made measurement in cemented houses and brick and mud houses. And this, you can see that how we deployed the instrument inside the houses. We tried all these methods for the measurement of the emanation, exhalation, or soil gas radon concentration, water radon concentration, everything. And then we made a table like this. This just a sample I'm showing you. I'm not discussing the result. That what is the radon concentration, what is the thoron concentration. And you will see that thoron concentration is very high here. If you take this particular example, 569 becquerel per cubic meter with the help of that radioid, and 484 is with the help of the Red 7. So we observed that this area is very high radon concentration. And of course, we published the papers in radiation protection dosimetry. And then, of course, in the Garhwal area also, you know that Garhwal area is very fragile area, very different type of the area, having a number of structures, and it is distinguished by this fault and thrust areas, many areas, and active fault because we have many earthquakes in that area. And you all are aware about that. What is the habitation in Garhwal town and villages of Garhwal? This, you can see the Srinagar and the other areas. This is the cemented houses which are built in the countryside, or you can say the villages. And these are some mud houses. And these are also some mud houses and wooden houses. This house, you can see the damaged house which are damaged during the earthquake. And these are some wooden house which are in that Purola area of Uttarkasi. And then later on, we got some values of the radon concentration. These are the values we measured like this: radon concentration, then attached progeny, and then unattached progeny, thoron concentration, equilibrium factor. These are many things. We have to do many things. And then finally, we come to the dose. What is the dose? And that way, you can find out that which area will have the major impact of the radiation. So I'm not going in detail because I just wanted to give you the flavor of the radiation, that what is the radiation and what are some important things we are doing in this field, especially from point of view of the radiation protection. And there are some other areas also, like we are working for the geological structures as well as for the earthquake study. But these are the environmental point of view or environmental radiation protection point of view, because later on we had collaboration with the Bhabha Atomic Research Center. And few years back, we have completed about 18 projects in North India. That is the collaborated research program. And here in Garhwal University, our lab was acting as a nodal center for that, because all projects are being collaborated from here. So we are trying to develop a country map of the radiation. So we have now done some survey in the North India, because that collaborative program was for the Jammu Kashmir, Himachal Pradesh, Uttarakhand, then Punjab, Haryana, Delhi, and Rajasthan and UP. So it was under our collaborative program. And then later on, there was some South collaborative program, in East also, in West also, and in Center also, they are doing that. So that way we will have a map of the radiation for the country. So I hope that within next few years, we'll get that map. But So far for Garhwal, we have already done it. Garhwal, Kumaon, also Uttarakhand, we have already done it. And all these results are published in one very important paper we published in Nature publication, that is the scientific reports. And this is in fact the first paper on radon-thoron study, which is published in the Nature publication. So it is an open access paper and anybody can see it, because everything we have given it, that is, you can just type the radon and the scientific report, you will find this paper from India. So with this, I think I would like to conclude, because I did not show any result here, but I just wanted to tell you that what is the radiation and how radiation affect the human being and what are some remedial action, and of course, just in brief that what are the work we are doing here. So with this, I would like to thank all of you for your patience and listening me. Thank you very much.
Thank you, sir. Sir, am I audible?
Yeah.
Sir, thank you for your valuable time. We have some queries from our participants. I want to read out for you.
Please.
Sir, the question is from Mr. Himanshu, that, sir, how the age of Earth has been calculated as 4.55 billion years.
This is based on the half-life of uranium, because the half-life of uranium is in the million years. And this is one radioactive dating. Of course, there are different types of the dating. I'm talking about the radioactive dating. And once, if you take a rock sample, that it contains the uranium. As I told you that uranium is always omnipresent. It contains uranium and it continuously decaying. So when it decay out, definitely it leaves some trace behind. That is in the form of the tracks in that particular mineral. And that can be measured by etching process or by some chemical process in the laboratories, that how many tracks are left. That means that gives you the number of decay. So that number of decay, based on the half-life, you can also calculate the number of decay. Now the thing is, it has, say, X number of the uranium atom. So Y number has already been decayed. Now, if you take the X number of the uranium, and if you expose it to the neutron, you know that with the exposure of the neutron, you get the fission reactions. So you have to expose it to the neutron. Of course, we use it in the Bhabha Atomic Research Center with the reactor. And then you get the total induced tracks. And by a calculation, there is one relationship. By using that fission and induced tracks, you can calculate the age of that rock, which is equivalent to the age of the Earth. And of course, there are some assumptions. It has been believed that with the formation of the Earth, that rocks was also formed. So this is the one method. Of course, there are many methods, Krypton method and some other methods are also there. But this is one of the methods to measure the age of the rock, or you can say the age of the Earth.
Thank you, sir. Sir, second question is from Mr. Guru Raj. How does radon emission rate vary with temperature?
This is really very good question. Radon emanation, there are two different things. So one should not get confused. One is radon emanation and other is radon transport. So emanation is basically based on the diffusion. So with radon emanation, what happens with the temperature, that atoms get loose, and this radon escapes very easily. Once it decays, it escapes very easily, and then radon emanation rate increases. And if there is a cold temperature, then it decreases. So that is why that it increases with the temperature, radon emanation.
Thank you, sir. Sir, another question is from Dr. Manisha. What is the principle people follow during measurement of radon and thoron?
What is the principle means? I could not follow the question. Is it about the methodology?
The scientific principle, yeah, that only. Methodology, yeah, sir.
It's a methodology because radon and thoron, they are alpha emitter. and we use the alpha detectors for measuring the radon and thoron. So like I told you that alpha guard, red 7, then radon ionization chamber, all these are the alpha detectors. So we detect the alpha particle and then measure the radon. Because radon itself, because radon is rear gas, it cannot be measured directly. But the quite important thing is that it is alpha emitter. So with that alpha, we can calculate the radon. This is
Thank
the
you,
basic
sir.
you say in terms of the principle.
Thank you, sir. Sir, we have another question from Tribhuvan Rana. What are the measures can be taken to reduce the radiation inside the house, or what building materials can be used to block the radiation?
It's if you say to reduce the radon concentration inside the house, the ventilation is the perfect method. You should have the well-ventilated houses. But sometimes, as I told you, in cold climate, ventilation is not that much frequent. And if you are in a city or in an urban area, it's quite easy because you can use the epoxy paint and some other material to protect the emanation of the radon from the building material. And but if you are in mud houses, then it seems a little bit difficult to protect yourself from the radon. That way, I don't know how to protect yourself from the entry of the radon. But in most of the houses in the urban area, they use the epoxy paint. Epoxy paint does not allow to radon to come out from the layer. And ventilation is, of course, for mud houses, you can say that ventilation is the only process. Otherwise, if you talk about our own country, we don't have that problem because we very often keep the room open. Our houses are very well ventilated. So we don't have that problem. But this is the main method. Main is the ventilation. And then second is if you want to protect from the building material, the epoxy paints are the better.
Thank you, sir. Thank you for your valuable answers. Now I would like to conclude the session. Respected everyone present over here, all the faculties, dignitaries, participants, and their students. I, Tripti Kumar, on behalf of organizing committee, entire fraternity of Nanhi Pari Simant Engineering Institute, convey deep regards to Professor Dr. R.C. Ramola, sir, for his vast knowledge on this topic, recent advances in radiation research, and his valuable time during this corona pandemic. Also wish my gratitude to our director, sir, Dr. A.S. Vidyarthi, for encouraging and support throughout the process. Special thanks to our convener, CMS Negi, sir, and co-convener, KC Das, sir, and whole organizing committee. I congratulate all the participants for their active participation and wish to see you all in the tomorrow's session at 4 p.m. Thank you all. Have a nice day. Thank you, sir.
Thank you very much. And I can see some of our colleagues like Dr. R.K. Sharma, Dr. Gunjan Purohit, they are also present here. And I must say hello to them also. And thanks to everyone for your patience and for bearing with me, I'll say. For some, it may be possible. But thank you very much. Thanks to all of you.
Thank you, sir. Sir, sorry for the inconvenience from our side.
No, it was in the beginning. I don't know what happens, but there was some problem with the audio and somebody was disturbing on that PowerPoint presentation.
Yes,
Yeah, but later on it went very smoothly.
Yes,
Thanks for everyone for cooperating.
yes, sir. It was just like radon emission.
Yeah, in between unusual radiation.
Everywhere in our screen. Thank you, sir. Thank you.
Thank you. Thank you very much. Thanks a lot. नेगी जी कहाँ है? नेगी जी नहीं दिखे मुझे।
बोलो यहीं से बोलो।
क्या बोलना?
अच्छा अब देखिए आप। चलो अच्छा था आपका, बहुत अच्छा था। It was really very nice. और कल अब फिर होगा, प्रोही जी का होगा।
कार्यक्रम में आने का धन्यवाद सर आपका।
धन्यवाद आपका बुलाने के लिए।
जी अच्छा रहा।
चलो कल प्रोही जी हैं शायद हैं कल।
हाँ जी सर जी सर
कल भी आएंगे, कल भी मिलेंगे।
जी सर।
ओके देन, थैंक यू वेरी मच
ओके,
वंस
प्रणाम।
और कल फिर मिलेंगे। थैंक यू।